In this example, we want to use a velocity field, an example of a vector field, to try to estimate the position of a particle that's been dropped in the velocity field after a certain amount of time. So, the first thing we should do is just think about what this means, that we have a velocity field. And this is a three-dimensional vector field, so we have every point in three-dimensional space. Let's just try to use the point we have. So at the point 3, 2, 1, so that point is kind of over here somewhere, we'll say. At this point P, the velocity field is going to attach a velocity vector to this point. Okay, really the velocity field has vectors attached at every point. There's just velocities everywhere. You can think of this as maybe a wind or something. But what we're going to do is say, okay, we've got this velocity field. For us, for our point, we're going to have to compute what is the actual velocity at this point P. So the first thing we should do is say, okay, we've got our velocity field. What's the velocity at our point P? And I'm using P to represent this point. So we're going to plug in the coordinates 3, 2, 1 for x, y, and z into our velocity field. And we're going to find that the velocity at this point of the wind, or whatever you want to think of this, but the velocity of the particle is going to be 3 squared, so 9, and then 1 plus 2 squared, so that's 5, and then the last one is 2 times 3 times 1, so that's 12. And so the velocity vector at this point is the vector in this direction, and I don't know, I'm probably not going to get it exactly right, but here's the velocity at P. Okay, and this vector then represents, so velocity is usually measured in, let's say, so this is our time, we're told, is measured in seconds. So let's say that it's measured in distance units per second, whatever this is. And so this is the number of steps that our particle would make in a full time step. Okay, so we want to make just 0.1 time steps. Now, in reality, the velocity changes from point to point. So what we want to do is we want to approximate the position of our particle after taking 0.1 second steps, right? So what we want to do is we want to head out our velocity vector in such a way that this represents just delta t equals 0.1 in some sense. So just a tiny, tiny step in this direction. Okay? And the new position of our particle will be about here. Now in reality, the particle will actually follow maybe some path that is so for which the velocity vector is tangent to it, but it might be curved, right? It might be curved. So we're really just going to get an approximation here. And so here's what we learn. We learn then that our position, so our new position at time t equals 0.1 or 0.1 seconds after we've dropped our particle here is approximately, and this is just like a linear approximation from earlier in this class or from calculus 1, but it is approximately then the position that it's at, so p plus 0.1 times our velocity vector here. So this is the delta t, right? So times v of p. And that's it. So this is our new position. Our position is approximately this much. All right. And again, if we think of, one way to think of this is that we have a position vector here, call it r, and that our point P is r of 0, and we want to approximate then r of 0.1. It won't be exactly this point, but it will be about our initial point, which is 3, 2, 1. Right, plus 0.1 times the vector that we just worked out. So 0.1 times this vector, 9, 5, 12. And of course, we should be thinking of our position as a vector as well. And all that's left to do is add this up. And so we end up with our new position should be about 3.9, and then 2.5. And finally 1 plus 1.2, so 2.2. Now again, our particle will not be at exactly this point, but this is an approximation of the position of the point using the velocity field that we were given. So this is how the velocity will affect the position of the particle.